Unit 6, Lesson 3, Accumulation Functions. Given some function y equals f of x is a continuous function on the closed interval ab shown below. Suppose we define some function whose area under the curve between point A and some other point x. We can denote the area under the curve as a definite integral. Let's define this as a new function, capital F of x, where x is in the closed interval ab. And so your capital F of x is going to be the integral from a to x, f of t dt. So for this one, it would just be this area right here because it's just from a to x. So that would be the definition of your integral. Your integral from a to x is going to actually be a number, which would be equivalent to the area under the curve from your function to the x-axis. So for any value of x between a and b, this new function will give us the area under f of t between a and x. This is the fundamental theorem of calculus part 1 and helps to make the connection between integrals and derivatives. Namely, that every continuous function f of x has an antiderivative, capital F of x. So the fundamental theorem of calculus part 1. If f of x is continuous on a closed interval ab, then g of x is equal to the integral from a to x f of t dt is continuous on that closed interval ab, and it is differentiable on the open interval ab. Also, the derivative of g of x is equal to f of x. So that part right there is probably the most important. That if I took the derivative of each side, I am going to get my function back. So if I take d dx of g of x and d dx of the integral from a to x f of t dt this is going to be g prime of x on this side, and the derivative and the integral are inverse operations. So they basically cancel each other out. What you need to do is put this in here, oops, and you get f of x, okay? So that's basically the biggest thing on that fundamental theorem of calculus part 1. So alternate notation can be seen by taking the derivative of both sides, which is what I showed you, and they changed g of x here to capital F, and it really doesn't matter what you call it. You probably just wouldn't want to call it little f if this was little f, okay? But you can see that, that big F prime is going to be equivalent to just plain old f of x, okay? So that is the fundamental theorem of calculus part 1. So what we have here is the graph of f is shown below. So this function here is f that we have. And let g of x be the integral from -6 to x f of t dt. Evaluate the following. So g of -3 is going to be the integral from -6 to -3 f of t dt. And so what that means is from -6 to -3, the answer to g of -3 is going to be the area under the curve. So however you want to split this up, we could split it up into a triangle, a rectangle, and a trapezoid and add those together. And just to remind you, area of our triangle is 1/2 base times height. Area of our rectangle is length times width. And area of our trapezoid is height divided by 2, base 1 plus base 2. Okay, so we're going to need to know this for these graphing ones. So for letter A here, we have 1/2 base of 2, height of 2. That's going to cover that area. We have a 1/2 rectangle. That's going to cover that area. And we have a trapezoid that has a height of 1, because look, that's your perpendicular distance between your parallel sides. And your parallel sides are 3 and let's say 2.5. So we've got 1 divided by 2 times 3 plus 2.5 is 5/2. And then we just need to add those up. Sorry, I'm trying to squish this in and it's running into everything. So this is 2 plus 2 plus, now this would be 6 plus 5 is 11/2, and that would be 11/4. So I have 4 plus 11/4, which would be 16/4 plus 11/4 would give me a total of 27/4. So g of -3 is 27/4, and it's basically that area from -6 to -3 under the curve, between the curve and the x-axis. G of 0 takes us, we've already got 27/4. It's going to take us, all the way to 0. So we need this area and this area to add on, and we'll have that. So g of 0 is going to be the integral from -6 to 0 f of t dt. All I'm doing is putting that 0 in where the x was in this function up here that they gave us. Okay? And so now I know I'm going to start with 27/4. That takes me from -6 to -3. And then I want to add on the area of this triangle and the area of this rectangle. So I'm going to say plus, this one's going to be 1/2. My base is 3. My height, it looks like is 1.5, which would be 3/2. And then plus, I've got a 1/3. So I'm just going to put 3. So I've got 27/4 plus, this is going to be 9/4, and then I might as well write my 3 as 12/4. And so that's going to give me 21/48, which is 12. So my g of 0 is 12. And now we've got g of 4. So that is the integral from -6 to 4 f of t dt. So now I think I'm going to choose a different color. We're going all the way to 4. And you can choose to split it up differently than me if you want to. I'm just, trying to see what would be the easiest, but it looks like here I'm going to be adding on a triangle and a rectangle. But since we're going from -6 to 4, we already have 12, because 12 is going to get us to 0. So then if we add on these two, we'll have our integral from -6 to 4. So I'm going to say that this is 12 plus, and then we have 1/2. Our base here is 1, 2, 3, 4, and our height is 1, 2, 3, 4. Now be careful, you don't want to count this down here because we're only talking about this triangle right here. So it's just 1, 2, 3, 4 height. And then plus, we've got a 1/4. So 1 times 4 is 4. So this one is going to give us 12 plus, we've got 8 plus 4. So that's going to be 24. So our g of 4 is 24. And lastly, they want us to calculate g of 7. So that's from -6 to 7 f of t dt. Try and get a different color here, about yellow. So that means I'm going to go all the way to here. And I'm going to, again, do a triangle and a rectangle. And I'm going to start with 24 because that's what we already know from -6 to 4 is 24. And then we're going to add on our 1/2. Our base here is 3. Our height is 1, 2, 3, 4. So 1/2, 3 times 4. And then plus, it's a 1 by 3. So 1 times 3 is 3. So we've got 24 plus 12 halves is 6 plus 3. So my G of 7 is going to be 33. So those are kind of fun. I hope you like those because, you know, you're using your stuff over here, your formulas, and I think that it's just a good idea to use those formulas. All right, so now let f be the graph of the function shown at the right, where capital G of x equals the integral from 0 to x, f of t dt. Complete the table of values for g. So there is a integral rule that if you're going from one number to the same number, I don't know what I have on here, but I need to turn it off. Oh, I have that on. Okay. Sorry about that, guys. But if there's an integral rule that says if I'm going from A to A, f of t dt, it's always going to be 0 because I'm going from, you know, one number to the same thing. You're not doing anything. You're staying there. Like if I said from 3 to 3, it's going to be 0. If I said from 2 to 2, it's going to be 0. Okay? So when we go to look at our input for this with our g of x being the integral from 0 to x f of t dt, if I say if I put a 0 in, g of 0 is from 0 to 0, my output is going to be 0 because I'm going nowhere. I don't calculate anything under that curve. But when I do g of 1, which means I'll put a 1 in for x, so I'm going the integral from 0 to 1 f of t dt, well then that's when I say, okay, here I just have this rectangle, and if I take 1 times 2, I get 2. It's above the x-axis, I get 2. So g of 2 is going to be the integral from 0 to 2. So now I'm going to add on this trapezoid. Do you see that that's a trapezoid? Hopefully you see that. And the height of your trapezoid here is your perpendicular distance between your parallel sides. So the height is going to be 1. So I'm just going to do this. Height is 1, so height divided by 2 times my base 1 is 2. Here's my base 1 right here, 2. My base 2 is 4. So this would be 1/2 times 6. So this is going to be 3. And maybe I'll do it in black just so you can see that that is equivalent to the area under that curve. We said 2 was what the area under this curve was. This thing doesn't like me today. There we go, 2. So you can see that if you add those up, you get 5. From 0 to 2 is 5. 2 plus 3. All right, so g of 3 is going to be the integral from 0 to 3. F of t dt. So now we're adding on this triangle. So to get that area, 1/2, the base is 1, that's down here, the height is 4. So 1/2 of 4 is 2. And so this area is going to be 2. So 5 plus 2 is 7. And now they jump to g of 6. And so that's the integral from 0 to 6. Well, we know the integral from 0 to 3 is 7, but I want you to listen very carefully. If your area is under the curve, because look, from 3 to 6 is all under the x-axis. We have to count that as negative when we are calculating our integral. So we know that this is going to be 7 and then minus whatever that area is from 3 to 6, okay? And so we can break it up like this. We could break it up into a triangle here and a rectangle here. So our triangle is going to be 1/2. The base is 2. The height is 2. Don't worry about the negative right now. You know, you're just going to try and figure out what that area is. And that area is 2. And then this would be 1 times 2. That area would be 2. So you have a total of 4 that is negative. So 7 minus 4, your integral from 0 to 6 is 3. And then g of 7 is the integral from 0 to 7. So now we need to find out what this right here is. So again, we've got a triangle, 1/2. The base is 1. And the height is 2. So this is just going to be 1. So this area is 1. So now we have, I'm just going to look at it as from 0 to 7. We have positive 7. Come on. And we have negative 5. So this answer is going to be 2. All right. So now, on what interval is capital G of x increasing? Well, if you look at it, it goes from 0 to 2, that's increasing. Then 2 to 5, that's increasing. 5 to 7 is increasing. The first time it starts decreasing is after 3. Okay, so it would be increasing on the interval from 0 to 3. Okay, so you see how that area under the curve is increasing as you go, but once it hits 3, now it's going to start decreasing. You could have also written it using interval notation 0, 3. Where does G have a maximum value? Well, it was increasing. It was 7 at 3, from 0 to 3. But then it started decreasing. So 7 must have been your maximum value. So you could say there is a maximum value of 7 at x equals 3. And then it wants you to sketch the graph. So we're just going to look at, the input-output is our xy. So the first one that we have is 0, 0. Then we have 1, 2. Then we have 2, 5. Then we have 3, 7. Then we have 6, 3. And 7, 2. And then you just want to kind of connect as best you can. Make it so that it's, rounded. You don't want to make it pointed. So you just kind of connect that curve, and that's the graph of G. Okay, so that's going to move us to our next page. Transforming the area accumulation function by altering its limits of integration. One thing that I want you to change in your notes is I would like you to make this k a 0 for right now, because we're going to analyze it from 0 to x, And then we're going to look at it from 3 to x, and then we're going to talk about what happens if it were k to x, like how the change in k, what that does to the graph of your function, okay? So hopefully you guys are okay with that, just making a couple of changes there. Just that one thing from 0 to x. So complete the table of values for the function capital F. So we know that capital F is the integral from 0 to x, okay, of that function f of t. And this is my function f of t right here, okay? So if I wanted to know what f of 0 was, my f of 0 is going to be the integral from 0 to 0, f of t dt. And I said that if you're really going nowhere, you're going to have 0. If it's 1 to 1, it's 0. If it's 2 to 2, it's 0. The next one would be the integral from 0 to 1, f of t dt. Okay? So if I look at that, it's this tiny little triangle here, and we said that we would calculate it 1/2 base times height. The base is 1, the height is 1. So 1/2, 1 times 1, that's going to be 1/2. And f of 2 would be the integral from 0 to 2, little f of t dt. And so that one is now, instead of adding on a trapezoid, I'm just going to go ahead and calculate that whole triangle there. So now we have a 1/2 2 times 2. So 1/2 2 times 2 is going to be 2. Now if we go to 3, do it in green. Oh, maybe not. Didn't get it. Okay. If we go to 3, I'm going to go ahead and do that triangle. And that is a 3 times 3, base of 3, 1/2 3, integral from 0 to 3, f of t dt equals 1/2 3 times 3. So that's going to be 9/2. Oops. Nine halves, that's 9. And then for 4, we're going to calculate this one, which is this whole triangle. It'd be a 4 by 4. So the integral from 0 to 4, f of t dt, is going to be 1/2 4 times 4. So 16/2 is 8. And there's our table. So what is the domain of f? Well, it looks like it is 0 to 10 is our domain. Those are all the x values that have an actual point on f of t. Use the concept of area accumulation to complete the graph of capital F. Plot your points in your table in blue. So I do have blue on right now, and they want me to plot the point 0, 0, 1, 1/2, which is kind of hard to see there, but I think you can see it. 2, 2, 3, 4.5, 4, 8. And I went ahead and connected those. So you can see how that is increasing, right? It's going to continue to increase until 6, and then it'll start decreasing, right? My capital F, because this what I just graphed right here was my capital F of x, and it's just going to keep getting bigger until 6. Then it's going to start coming and decreasing. where is the 0 of capital F? So where do you think that 0 is? I've got definitely at x equals 0, there is a 0. What is the total change in F? And on my paper, when I did this on the last video that you couldn't hear what was going on, which of course is annoying, I went ahead and filled in the rest of my values. So what I did was I also looked at it at 6 and at I think I did 6 and 8 and 10. So I just want to let you guys do that also, because I think it does help whenever you're trying to answer some of these questions, because then you can get a good idea of what your capital F looks like. So if I wanted to find out what the integral from 0 to 6 f of t dt was, I would be taking my 8 and I would add on the area of this triangle. That would take me all the way to 6. And so the area of that triangle, and I'm just going to move this over a little bit, this is going to be, like I said, 8 plus, and then this would be 1/2. The base is 2, the height is 4. So 8 plus 4 is 12. So this is going to be the 0.6 comma 12. And if I went to 8, this would be from 0 to 8, f of t dt. And I already know that from 0 to 6 is 12. But then if I look to 8, I would have to subtract the area of this triangle. So this is going to be minus 1/2, and this would be 2 and 1, 2, 3. So this would be 2 times 3. So 12 minus, this would be 3. So this is going to be 9. And then if I put a 10 in, the integral from 0 to 10, f of t dt, I know that I have 9 all the way up to 8. And then I have another negative, so minus, and then this would be a base of 2 and a height of 3. So 1/2, 2 times 3, that's going to give me 9 minus 3, which is 6. So if I do that, and then, I think I was in that blue, and I start graphing these, so at 6 I had 12, at 8 I had 9, and at 10 I had 6. I could kind of follow that, you know, and you want it to be like smooth. You don't want it to go abruptly like in a point at all. You want to smooth it out. It's just a smooth curve, okay? But there's the rest of your capital F. So when you say what is the total change here would have been your capital F of 10 minus your capital F of 0. Because that would have been your total change in F. You were talking about, you know, those y values. Our capital F of 10 was 6 minus our capital F of 0 was 0. So our total change is going to be 6. So that answer for E is 6. And then how does the total change in F compare to the net area bounded by the graph of the function f and its x-axis? So it ends up that they are the same, because if I got all the way to 10 here and looked at, you know, what my 0 to 10 was, it was 6, and my net change in capital F was 6. So I'm going to say they are the same. What is the maximum value of F? Well, remember the maximum was going to occur at 6. So at 6 we had 12. So our maximum value of f is 12. And where does it occur? At x equals 6. What is the range of f? Well, on the y-axis, it goes from 0 all the way to 12. So our range would be 0 to 12. You could also write it as that, okay? If you wanted to write it, using your variable y. All right, example number 4. Now consider the function g of x equals the integral from 3 to x f of t dt. And what is the 0 of g? So what could I put in here that I would then put in here that would make this equal to 0? Hopefully you are going to say 3. Right? Because if I go from 3 to 3, that's going to be 0. And then what is g of 0? Well, g of 0 is going to be the integral from 3 to 0, f of t dt. Well, this always has to be smaller number to a larger number. If it isn't, if your smaller number is not on the bottom, so let's just say that this was the integral f of t dt. So if it went larger, smaller, so if that was your integral, you have to set it equal to the negative of the integral, smaller, larger, before you can do anything, okay? So please remember that, because when I'm going to solve this g of 0, I would have to make it the negative of the integral from 0 to 3, f of t dt. And so for that one, we are still on this graph. So from 0 to 3, we said that was 9/2, but now g of 0 would be negative 9/2 because of how they've defined big G. Big G starts at 3 and goes to x, f of t dt, okay? And so, and in fact, I'll probably erase that because I don't want to get you confused. You always have to know what your function is. If this is your function, g of x, then when you calculate g of 0, you're putting a 0 in up there for x. And, if it's not smaller to larger, you got to put a negative in front of it and flip those. And so that's going to give you that negative value. What is the domain of g? So how would we figure out our domain here? Well, it's the same function. It's integrating f of t. So my domain is going to be the same from 0 to 10 because I'm integrating the same function up here, just like we did on capital F. Now we're doing capital G. And the only thing different is that capital F started at 0 and went to x of this function, and capital G starts at 3 and goes to x of this function. And we already saw how our g of 0, because of it starting at a different point, is going to be very different for, for your g function than it was for your f function. What is the total change in g? Well, that's going to be your lowest to highest, right? So what I did, because they're going to be asking us to sketch the graph of g, and they didn't really give us a place to do the chart. So what I would like to do is have you guys somewhere fit in a g chart where you've got your x value and you're going to have your g of x value so that we can plot these points. And we already said, well, if we started at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh my gosh, this is going to be a lot of work. But we already said that our g of 0 was negative 9/2. Okay. So now our g of 1, I just want one that will write for me, is going to be the integral from 3 to 1 f of t dt. Notice that that's going to be the negative of the integral from 1 to 3 f of t dt. And so if I look and I saw from 1 to 3, it's actually a trapezoid. And that trapezoid, I'm just going to redraw it right here so I don't get everything mixed up. But this is your height of your trapezoid, which is 2. And your base 1 is 1. And your base 2 is 3. So this is going to be negative, and it's going to be height divided by 2 times base 1 plus base 2. So this is going to be negative 4. So for x equal 1, our g of 1 is going to be negative 4. So now let's do g of 2. This is the integral from 3 to 2. F of t dt. Hopefully you notice that you're going to have to take the negative of the integral from 2 to 3. F of t dt. And if I go from 2 to 3, I have another trapezoid. The height of this one is going to be 1. Our base 1 is 2. Our base 2 is 3. So this is going to be negative, and this is going to be height divided by 2 times base 1 plus base 2. So negative 5/2. And then our g of 3, we said was 0. Our g of 4 is going to be the integral from 3 to 4, f of t dt. So from 3 to 4, we have another little trapezoid. It has a height of 1. And at 3 we have, so the base 1 is 3. At 4 we have 4, so base 2 is 4. So this is going to be height divided by 2 times base 1 plus base 2. That's going to give me 7/2. Our g of 5 is going to be the integral from 3 to 5, f of t dt. And so from 3 to 5, you have like 2 different trapezoids. So you've got a trapezoid here, and then you've got a trapezoid here. So we would have to add up those trapezoids. Each one has a height of 1, and the one from 3 to 4, we said was 1/2 3 plus 4, because that was this one. And then plus 1/2, this is going to be 4 plus, and if we go up here at 5, we have 2. So that's going to be 4 plus 2. So this is going to be 7/2 plus 6/2, I guess. I was going to say 3. I almost wrote a 3, which is going to be 13/2. So for g of 5, we would have 13/2. And now I'm going to move it so that I can do it over here. Our g of 6 is going to be the integral from 3 to 6, f of t dt. And so from 3 to 6, it looks like we have a trapezoid from 3 to 4, right? And that we know from 3 to 4 is 7 halves, plus a triangle from 4 to 6. And so that would be 1/2. The base of that triangle is 2. The height of that triangle is 4. So we have 7 halves plus 8 halves would give us 15 halves at 6. And our g of 7, integral from 3 to 7, f of t dt. Well, we know that from 3 to 6 is 15 halves. So now I just need to add on 6 to 7, and it's negative. So I'm going to be adding on a negative, I got to make that bigger, 1/2, 1 times 3 halves, because it looks like that from 6 to 7, it would be 1/2 base times height would be 1/2 times 1 times 3 halves for the height. So we've got 15 halves minus 3/4, going to give us 27/4. Our g of 8 is going to be the integral from 3 to 8, f of t dt. We already know that from 3 to 7 is 27/4. Now we just need to add on from 7 to 8, and that is a negative trapezoid. If you can see, we've got a trapezoid that looks like this. This is height of 1, right? That's your height. And then at 7, you have 3 halves. And at 8, you have 1, 2, 3. You don't want to do negative, even though we're going to add on a negative, but when we're calculating the area, we want to do it as a positive. Just because it gets too confusing, I think. Well, I mean, you could. I'm not saying it's wrong. I'm just saying that's why I'm not doing it. I think it gets too confusing when you're doing it like that. So this is going to be 27/4 minus, and if I made that 6 halves plus 3 halves, that'd be 9 halves. So this is a negative 9/4. So this is going to give us 18/4, which is 9 halves. And then our g of 9, I've got 9 halves, right? Or, well, I guess I forgot to write the integral from 3 to 9. Sorry about that. This is our integral from 3 to 9, f of t dt. And we already know that integral from 3 to 8 is 9 halves. Now, what about from 8 to 9? So, again, we're negative, and it's a trapezoid. And it looks like this time. So we're going to subtract, has a height of 1, and this is going to be 3 here, and it looks like 3 halves here. So minus 1 divided by 2 times 3 plus 3 halves. So I've got 9 halves minus, this is going to be 9/4. And so this would be times 2 would give me 18/4 minus 9/4 is going to be 9/4. So I've got 9/4 at 9. And then lastly, my g of 10. Integral from 3 to 10, f of t dt. And so I know that from 3 to 9 is 9/4. And from 9 to 10 is just a little triangle, so I'm going to subtract the area of that because it's under the x-axis. And from 9 to 10, it's going to be a 1 by 3 halves, so 1/2 times 1 times 3 halves. 1/2 times 1 times 3 halves. So 9/4 minus 3/4 is going to be 6/4, which is 3/2. So at 10, we have 3/2. They're going to want us to sketch this in green. So I'm going to get my green marker, and I've got my points here. 0, 4.5 is my first point, and then 1, -4, and then 2, -2.5, and then 3, 0, 4, 3.5, 5, 6.5, 6, 7.5, 7, 6.75, 8, 4.5, 9 is 2 1/4. Oops. And 10 is 1.5. So if I connect these with a smooth curve, does it look familiar? Isn't that just a vertical shift downward? 4.5 of your f of x. So I wanted you in the beginning to start thinking about what it does to change that bottom number. Okay, and we had 0 here as our bottom number, and we had 3 here as our bottom number, and it ended up giving us a vertical shift of the exact same function. And so when it says what is the total change in g, if I took my g of 10 minus my g of 0, it would give me 3/2 minus -9/2. And so that's 3/2 plus 9/2, which is 12/2. Uh-oh, it's 6. So that is going to be the same total change as it was in F. And what is the maximum value? Well, that's going to be the whatever it is at 6. And we said at 6 it was 15/2. So our maximum value for G is 15/2. And it occurs at x equals 6. The range, well, my lowest y value is -9/2. My highest y value is +15/2. So it's going to be -9/2 to +15/2. And then we did already sketch it. So I took care of that one. I wanted to sketch it. I'm a visual person, so I wanted to show you what that looked like before we started answering some of these questions, because I felt like it made more sense to do it that way. So now I describe the relationship between all capital F of x equals some k to x f of t dt as k takes on different values. So hopefully you guys saw and were able to feel comfortable that all your f of x's are going to be vertical shifts of one another. So all capital F of x's are vertical shifts of one another. What point must lie on the graph of any given family member and why? Well, I notice up here that when the 0 was at the bottom, 0, 0 was on my graph. When the 3 was at the bottom, 3, 0 was on my graph. So I hope that you kind of are getting the idea that if that was your k to x, if my x was k, I'd get 0. So that would be the point, k comma 0. And so I would say k comma 0 would lie on any graph. Comma, because when the lower bound is k, the area from k to k is 0. Okay, so hopefully that makes sense and you can see what I mean by that. As k takes on different values, the functions capital F of x equals k to x f of t dt graph as, this would be vertical transformations of one another, each containing the particular point k comma 0. And even though the lower bound changed, is f prime equal to f of t. So if I took and went back up here and looked at my f, and then this one I did not label it, but that was my g, are these going to have, are f and g going to have the same derivative? Like if I took, you know, the slope of the tangent line here, is it going to be exactly the same as the slope of the tangent line here? Yes. If I took the slope of the tangent line here, is it going to be exactly the same as the slope of the tangent line here? Yes, they're both going to be 0. See how these derivatives, which are slopes of tangent lines, are going to be parallel? So they're going to be the same for these two. These are parallel. If I took the derivative over here, it's going to be the same as the derivative over here. Those are going to be parallel. So it's asking, even though the lower bound changed, is f prime of x equal to f of t? And your answer is going to be yes. And remember, when we take the derivative of it, it kind of cancels it out. So, both of these, if we took all the derivatives, it's going to give you this function right here in black. That is your derivative function for both of these because of the way we did this. Okay, so this f of t here, and you could say it's f of x because there's an x here, so you could say technically that would be f of x. If you wanted to change that to, if that made you feel better, it kind of makes me feel better to put an x there. But this black function that we started with here is the derivative of both of these other functions. Is that crazy or what? Okay, so now, example number 5. Shown below is the graph of the derivative f of some function capital F. Assume capital F of -3 is -8. What I think I'm going to do right now is go ahead and stop at this point and then try and download or upload this video. I don't know how long I've been talking, but it seems like a while. And then I'll start it up again.